Today on How It's Made. Steel safes, false teeth, airplanes, and maple syrup. The first bank safes were made of wood reinforced with sheet iron. Thieves would just smash them open. Then came safes made of solid iron. Thieves would just blow them up. But then, to the crooks' dismay, came safes made of steel. It all starts with sheets of solid steel up to 3.5 centimeters thick and an automated machine with an oxygen and gas-fueled flame. The flame slowly cuts the plates that will form the walls of the safe. The cutting creates gases that are doused with water. A welder with a manual version of the same flame frees up the plates with a few last cuts. Then, using a large magnet, they stack the plates. Each one is labeled so the workers will know in what order to assemble them. They're assembled by a welder who uses a semi-automatic soldering gun. The solder is a special welding wire made of several different metals. It rolls off a spool as needed. Elsewhere in the factory, a semi-automatic saw cuts flat bars of steel. These bars will form the frame that'll surround the steel plates. Meanwhile, another machine, called a turret, fashions steel bars into moving parts for the locking mechanism, and also into hinges. That milky liquid is a lubricant. Normally, you see raw material move on an assembly line from tool to tool. This is just the opposite. The steel bar stays on the turret from start to finish. The tools come and go. Workers take pieces of sheet metal cut into shapes by laser and bend them in a press to make various parts and mechanisms. Meanwhile, the large steel plates they cut earlier go into a hydraulic press to make them perfectly flat. It's finally time to put all the components together. They construct the frame in an assembly jig, then insert the plates for the sides, top, and bottom. Using the semi-automatic soldering gun again, they fuse the pieces together. They measure the angles, then use a giant clamp to square the safe. Finally, they install the plate for the back of the safe and solder the joints. They stand the safe upright and grind down the soldering lines until they're smooth. This factory also produces what's called a composite safe, made of soft materials such as copper, aluminum, and low-grade steel. But it has a cement core, making this safe harder to break into. The finished safe gets 3 coats of paint. Then in the finishing department, they install the mechanical or electronic locks and locking mechanisms, as well as the internal time lock mechanism. The time lock allows access to the safe only at certain times of day, such as the bank's business hours. Even if someone picks the outside combination locks, the door won't open outside those set hours. The machines that sterilize medical instruments use ethylene oxide, a highly toxic gas. Now, there's a new method that's safer, more effective, and less expensive. This new machine uses ozone as the sterilizing agent. Ozone is a form of oxygen. Until the 1800s, false teeth were made of animal bone, ivory, or actual human teeth. They came from poor people who sold their teeth and from dead bodies. Today's dentures are usually ceramic. They start by heating a sheet of wax over a flame. They press it onto a rough plaster model of the patient's mouth sent in by the dentist. The lab technicians use this model to prepare what's called an impression tray, what the dentist will use to make a rubber mold to cast the dentures. They apply an acrylic material over the wax lining, forming a handle so they'll be able to remove it afterwards. Once the acrylic hardens, they pull it out of the model and discard the wax. The dentist fills this new acrylic tray with rubber to take a final impression. The lab uses the hardened rubber as a negative mold of the patient's mouth. They fill it with plaster to make a new, more precise plaster model. Then they use the new model to make the part of the dentures that fits on top of the patient's gums. They take special orthodontic acrylic and press it into the model to form what's called the base plate. Then they heat a sheet of wax to form a rim on the base. This new acrylic and wax model now goes back for another fitting in the patient's mouth. The dentist takes a series of measurements to show the lab exactly where to place the teeth. The model goes back to the lab, where technicians select the teeth that'll best suit the size of the patient's mouth. They install the teeth one by one into the model's wax rim. Then they send the model back to the dentist for the final fitting. The dentist checks that everything is centered and that the patient's bite is properly aligned. If the model fits well and looks good, the lab can finally begin to manufacture the dentures. They position the model in a special holder called a flask, then attach channels through which acrylic will later be injected. This acrylic will replace the wax holding the teeth in place. But first, to get rid of the wax, they have to cast a plaster mold to hold the teeth in place. Once the plaster dries, they submerge it in hot water for 5 minutes to melt the wax inside. They rinse the plaster mold with warm water to remove any wax residues. Then they apply what's called a separator, a chemical that will keep the acrylic from sticking to the plaster mold, just like greasing the pan when you're baking. They position a cylinder of acrylic right over the flask. Using an air pressure piston, they force the acrylic into the plaster mold. They submerge the mold in boiling water for 35 minutes to harden the acrylic. Once the flask has cooled down, they break the plaster. The false teeth are now securely rooted in acrylic gums. A bit of finishing and they'll be done. An ultrasonic bath gets rid of any remaining plaster. They polish the acrylic with pumice, then shine it up with a polishing compound. The set of false teeth is finally ready. When a patient doesn't need a full set of dentures, just a few teeth, they get what's called a partial, made much the same way, but hooked on at either end to the patient's natural teeth. Aviation was once the exclusive domain of commercial and military pilots. Not anymore. Today, many amateurs get their pilot's license and take to the skies in light aircraft. Not for a job, but for the sheer pleasure of flying. To construct the body of these light aircraft, they start with two types of cloth. One woven from glass fibers, fiberglass, the other from carbon fibers. Carbon is a chemical element that's stronger than steel. Both materials go through a laminating machine that coats them with an epoxy resin. To begin forming the various parts that make up the body, workers lay strips of the laminated fabric into molds. The engineering plans dictate the precise positioning of the strips, which is critical for strength and durability. They lay in carbon fiber cloth where they need to have extra strength without additional weight. Areas such as this, the passenger compartment of a cockpit. To make the fuselage, they sandwich a foam core about 10 millimeters thick between two layers of the fiberglass cloth. The foam also insulates against heat, cold, and noise. Workers coat the edges and joints with resin, filling any voids. Once all the fabric is in the mold, it's time to vacuum bag it. First, they cover everything with a layer of perforated plastic. Then with a breather cloth, which looks like a white wool blanket. Then comes another layer of plastic. They attach a vacuum to suck out all the air. The excess resin exits through the tiny holes in the plastic and soaks into the breather cloth. Now that the mold is airtight, it can begin to cure. They put it into an oven at 40 degrees Celsius for 8 hours. Once the molds come out of the oven, workers install the internal structure. Then, using the same epoxy resin they used earlier to laminate the fiberglass and carbon fiber fabrics, they bond the tail's upper and lower shells together. They do the same with the wings. The parts are left to cure overnight. The next day, they finally come out of the molds. Next stop, the trim shop. Workers remove the excess fiberglass and cut out the windows. The parts go back for a final curing. The oven is 80 degrees Celsius, twice as hot as last time. 18 hours later, out they come for painting. Workers sand the parts and coat them with an epoxy primer first. The finish coat is a polyurethane which resists weathering. Meanwhile, other workers assemble and test various components, such as the electrical system. A computer guides a machine to cut all the metal parts, such as the instrument panel. The cutting machine doesn't have a blade, but rather a sand and water jet that's powerful enough to cut through metal. A certified aircraft welder prepares the engine mount, the base that will hold the engine in place. It's made of high-grade carbon steel. At the final assembly stage, workers install the engine and other previously assembled components into the fuselage. Workers position the wiring and plumbing, then hook them up. They screw on the wingtips, which already have their navigational lights. An avionics technician powers up the airplane for the first time to function test everything. The final inspection takes place where it really counts, in flight. How do maple trees make sap? They accumulate starch during their growing season. With the spring thaw, enzymes transform the starch into sugar. When the trees absorb water through their roots, it mixes with that sugar to make sap. Long before the white man came to North America, the native Indians revered the maple tree. In early spring, they'd pierce its trunk with a tomahawk, then place a wood chip under the hole to channel the sap into a bark container. Then they boiled the sap over a fire in clay pots. The Indians introduced maple syrup to the European settlers. Today, most producers use tubing instead of sap buckets. No more trudging through the snow from tree to tree. The time to collect sap is in the early spring, when the maple trees are still dormant and when the temperature hits 3 or 4 degrees above freezing. The freeze and thaw cycle alters the pressure inside the tree and starts the sap flowing. The first step is to tap the trees. They drill a hole 1 centimeter in diameter, 5 centimeters deep. Then gently insert a spout made of metal or plastic. It's important not to damage the bark. That not only harms the tree, but also lets air in the sap, which ruins the flavor. You don't see too many sap buckets around anymore. Today, sap is pumped through polyethylene tubes to larger collector tubes. Then into the pumping station. Sap is 97.5% water and only 2.5% sugar, so to transform the sap to syrup, they have to boil it down. It takes 40 liters of sap to make just 1 liter of syrup. When the tank fills up, the sap is automatically pumped to the sugar house into a stainless steel tank. The more advanced producers use a specialized machine that partially concentrates the sap by reverse osmosis. This more than triples the sap's natural sugar level and means they'll have less boiling to do. From there, the sap flows to the evaporator. They heat the sap to the boiling point and keep it boiling however long it takes to evaporate 66% of the water. If the water evaporates too slowly or too quickly, that'll adversely affect the color, flavor, and texture of the syrup. However, and here's where expertise is everything, there's no set cooking time. Experienced maple sugar producers can tell when it's ready just by looking at it. They test the sugar level using a device called a hydrotherm. When the syrup is just right, they run it through a pressure filter to remove calcium residues and other impurities. They store the syrup in steam-cleaned barrels. The lab at the central warehouse tests a sample from each drum. Using sophisticated instruments, technicians classify the color from dark to extra light. They also assess the quality. Lower grade syrup is for industrial use, higher grade for the retail market. They pasteurize this syrup, then put it into huge stainless steel storage tanks. The tanks are vacuum sealed with a nitrogen barrier to preserve the flavor and color and to prevent fermentation. It also keeps the syrup from crystallizing. The lab then uses an instrument called an atomic absorption spectrophotometer to analyze the syrup's mineral content, making sure it meets market standards. Next, they warm the syrup in stainless steel heaters and run it through industrial-size filters. This step ensures the syrup will be perfectly clear. Then, just before bottling, they heat the syrup again, this time to 82 degrees Celsius. This not only sterilizes the bottles, but also guarantees the syrup will have a 4-year shelf life. Maple syrup is high in sugar but has somewhat fewer calories than honey or brown sugar. It's 100% pure and natural, and it's a good source of 3 essential nutrients: calcium, potassium, and magnesium. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.